Welcome to the deep dive. Today, get ready to explore the amazing world of hearing. We're going to kind of unlock the secrets of how your ears work. From the basic physics of sound all the way to that intricate machinery inside your inner ear. Our guide for this journey is a fascinating physiology handout by Dr. Rasha Eldeeb. It's packed with like mind-blowing details. For example, did you know your ears can generate their own electrical signals and that your ears have like built-in protection mechanisms to shield them from those loud noises?
That's right. It's a truly remarkable system.
Okay, so let's unpack how sound actually travels to our ears. What's like the basic physics behind it all?
Well, sound travels as pressure waves,
Mm.
kind of like ripples spreading out when you drop a pebble in a pond. These waves have two key characteristics, frequency and intensity.
So frequency is what we perceive as pitch, right? Like the difference between a low rumble and a high-pitched squeal.
Exactly. We measure frequency in hertz, and the average human can hear an impressive range of sounds from about 20 to 20,000 hertz. That's everything from the lowest bass note on a piano to the highest whistle you can imagine.
Wow, that's a pretty wide spectrum. But what about intensity? How does that factor into what we hear?
Intensity relates to the loudness of a sound. We measure it in decibels. To give you a sense of the scale, a whisper might only register at around 10 to 40 decibels. But a jet engine taking off, that could hit a deafening 160 decibels.
It's amazing how much variation there is in the sounds we experience every day. And here's something that I always find surprising. Sound can't travel in a vacuum. It needs a medium, like air or water, to propagate. It's different from light in that way.
That's a great point. And when sound hits an extreme intensity of 180 decibels,
Yeah.
it becomes so powerful that your body absorbs it and converts it into heat energy.
That's wild. Okay, so we've got these sound waves traveling through the air. How do they actually enter our ears and get transformed into, something that our brains can understand?
That's where the incredible design of the ear comes in. It's this remarkably sophisticated system that captures, amplifies, and translates sound waves into electrical signals. It's a bit like a three-part symphony, didn't you say?
I like that analogy. You've got the outer ear, the middle ear, and the inner ear, each playing a crucial role.
Exactly. The outer ear, with its distinctive shape, acts like a funnel. It collects those sound waves and channels them toward the eardrum, which vibrates in response.
Then the middle ear steps in to amplify those vibrations. It uses a chain of three tiny bones, the malleus, the incus, and the stapes. I remember learning their names in school, but it's amazing to think about how they actually work together.
It really is. Imagine the middle ear as a finely tuned drum, amplifying sound waves by an incredible 22 times before they reach the inner ear.
Wow, 22 times. That's a significant boost. And speaking of the inner ear, that's where things get really complex, right? It's home to the cochlea, this spiral-shaped organ that's often described as the microphone of the ear. But it seems like it does so much more than just capture sound.
You're right, it's far more than a simple microphone. The cochlea is where the magic happens. It converts those mechanical vibrations into electrical signals, which your brain can interpret as sound.
But how does that conversion actually work? It sounds incredibly intricate. Can you break it down for us?
Absolutely. The cochlea is filled with fluid and is divided into three main chambers: the scala vestibuli, scala media, and scala tympani. And within the scala media sits the organ of Corti, the true heart of hearing.
So the organ of Corti is like the command center of the inner ear.
Exactly. It contains two types of hair cells: inner hair cells and outer hair cells. The inner hair cells are the primary sound receptors. They detect those subtle vibrations and convert them into electrical signals. But the outer hair cells are fascinating too. They play a crucial role in fine-tuning the sensitivity of the inner hair cells.
Hold on a minute. How do they do that? Fine-tune sensitivity.
Here's where it gets really interesting. Unlike most cells in your body, the outer hair cells can actually contract, like tiny muscles. These contractions actually amplify the vibrations of the basilar membrane, making the inner hair cells much more sensitive to sound. It's a remarkable feedback loop that allows us to distinguish between very subtle differences in frequency, like the nuances between musical notes.
That's incredible. I never knew that these tiny hair cells were so dynamic.
It's one of the things that makes the auditory system so fascinating.
Mm-hmm.
There's a lot more to it than meets the eye, or rather the ear.
So these hair cells are translating those amplified vibrations into electrical signals. How does that actually happen?
Well, the cochlea is not only filled with fluid,
Mm.
but it's also buzzing with electrical activity. There's a difference in electrical charge between the fluids inside the different chambers of the cochlea. We call this the endocochlear potential.
Wait, so there's like an electrical potential built right into my ear?
Yes, it's remarkable, isn't it? And this endocochlear potential is crucial for the hair cells to function properly.
Okay, I'm hooked. Tell me more about this endocochlear potential.
Think of it this way. The cochlea is like a tiny battery with a positive and negative pole. This electrical gradient allows the hair cells to convert mechanical vibrations into electrical signals.
So the hair cells are basically bridging the gap between these two electrically charged fluids.
Exactly. As the basilar membrane vibrates in response to sound, the hair cells bend, causing tiny channels to open up. This allows potassium ions to rush into the hair cells, depolarizing them and triggering the release of neurotransmitters.
So it's like a chain reaction, starting with the vibration of the eardrum and ending with the perception of sound in our brains. It's mind-blowing how this all happens so quickly and seamlessly.
It really is. And we're just getting started. Now that we've seen how these electrical signals are generated, we can follow them on their journey from the ear to the brain, tracing the path of sound as it makes its way into our consciousness.
That sounds fascinating. Let's dive into that in part 2 of our deep dive into hearing.
Welcome back to the deep dive. Before the break, we were just starting to unravel the electrical symphony happening inside your ears.
It's amazing to think that something as seemingly simple as hearing involves, all this complex electrical activity.
It really highlights how sophisticated our sensory systems are. So let's trace the path of those electrical signals as they journey from the ear to the brain, where they're ultimately interpreted as sound.
Sounds good. Where do we begin?
The journey starts with the spiral ganglion, a cluster of nerve cells located right inside the cochlea.
So the spiral ganglion acts like the first relay station gathering all those signals from the hair cells?
Exactly. From there, the signals travel to the brain stem, specifically to a region called the cochlear nuclei.
And what happens at the cochlear nuclei?
This is where things get really interesting. The cochlear nuclei don't just passively pass along the signals, they start to process them. Different groups of neurons within the cochlear nuclei respond to different frequencies, helping to break down the complex sound information into its component parts.
That makes sense. It's like sorting the mail before sending it on to different destinations.
That's a great analogy. From the cochlear nuclei, the signals are relayed to another important processing center in the brainstem called the superior olivary nuclei.
Okay, and what's special about the superior olivary nuclei?
Well, these nuclei receive signals from both ears. And here's the fascinating part. They can compare tiny differences in the timing and intensity of the signals coming from each ear.
Wait, so that's how we can tell where a sound is coming from. Like if a car horn honks on my left side, my left ear will hear it slightly sooner and slightly louder than my right ear.
Precisely. The superior olivary nuclei are able to detect those subtle differences and use that information to pinpoint the location of a sound in space. It's a remarkable feat of neural computation.
It really is. And it happens so effortlessly that we just take it for granted. So where do the signals go after the superior olivary nuclei?
From there, they continue their journey up the brainstem, passing through a bundle of nerve fibers called the lateral lemniscus.
And the lateral lemniscus just acts like a highway carrying the signals along.
Yes, it's a major pathway for auditory information. The signals then reach the inferior colliculi, located in the midbrain.
Okay, and what happens at the inferior colliculi?
These structures are involved in a lot of important auditory functions, including something called the auditory startle reflex.
You mean like when you jump at a sudden loud noise?
Exactly. The inferior colliculi receive input from other parts of the brain, including areas involved in processing visual information and detecting potential threats. They help to coordinate a rapid response to unexpected sounds that might signal danger.
So it's like a built-in alarm system constantly monitoring the soundscape for anything unusual.
That's a great way to put it. From the inferior colliculi, the signals are relayed to the medial geniculate body, which is part of the thalamus.
Okay, I remember learning about the thalamus. It's like a central relay station for all sorts of sensory information, right?
Exactly. The medial geniculate body is specifically involved in processing auditory information. It acts as a gatekeeper, filtering and organizing the incoming signals before sending them on to their final destination.
And that final destination is?
The auditory cortex. It's located in the temporal lobe of the brain, and it's where those electrical signals are finally interpreted as the sounds that we perceive and understand.
So the auditory cortex is like the grand concert hall where the entire symphony of sound comes together.
I love that image. It's in the auditory cortex that all those different aspects of sound pitch, loudness, location, timbre are integrated into a coherent perceptual experience. And different regions of the auditory cortex are specialized for processing different types of sounds like speech, music, or environmental noises.
It's amazing to think about all these different brain regions working together so seamlessly to create something as fundamental as hearing. But there's one more important detail we need to talk about, right? Bilateral representation.
You're right, it's crucial. Remember how the superior olivary nuclei receives signals from both ears? Well, that's just the beginning. As the signals travel up the auditory pathway, they're constantly being shared between both sides of the brain.
So it's not like one ear is wired to just one side of the brain.
Not at all. This bilateral representation is a brilliant redundancy mechanism. It means that if one side of the auditory pathway is damaged, you'll still be able to hear with the other ear.
That makes a lot of sense from an evolutionary perspective. Our ancestors couldn't afford to lose their hearing completely if one ear got injured.
Exactly. And beyond providing a safety net, this bilateral representation also helps us to better localize sounds and differentiate between sounds coming from different directions. It creates a richer and more nuanced auditory experience.
Well, this entire journey of sound, from the outer ear all the way to the auditory cortex, has been truly fascinating. It's made me appreciate the complexity and fragility of this incredible sense.
Absolutely. And speaking of fragility, let's shift gears and talk about what happens when things go wrong, when this intricate system malfunctions,
Yeah.
leading to deafness.
That's a good point. We briefly touched on the two main types of deafness, conductive and nerve deafness, but let's delve a little deeper into their causes and consequences.
Conductive deafness, as we mentioned earlier, occurs when there's a problem with the transmission of sound waves through the outer or middle ear. It's like having a blocked pathway, preventing those vibrations from reaching the inner ear.
Right. So it's a problem with the mechanics of sound transmission, not with the inner ear or the auditory nerve itself.
Exactly. Some common causes of conductive deafness include things like earwax buildup, which can obstruct the ear canal, fluid in the middle ear, often due to ear infections, and a perforated eardrum, which can be caused by loud noises or trauma. Also, damage to those tiny bones of the middle ear, perhaps from an injury or certain diseases, can lead to conductive hearing loss.
So there are quite a few things that can go wrong in the outer and middle ear, but what are the typical consequences?
Well, the most obvious consequence is a decrease in hearing sensitivity. Sounds will seem quieter, and you might have trouble understanding speech, especially in noisy environments.
But the good news is that conductive deafness can often be treated, right?
That's right. The treatment depends on the specific cause, but it could involve something as simple as removing earwax or as involved as surgery to repair a perforated eardrum or reconstruct the bones of the middle ear.
That's reassuring to know. But what about nerve deafness? Is there any hope for restoring hearing in those cases?
Nerve deafness is a bit more complex and unfortunately often more challenging to treat. It results from damage to the inner ear, specifically to those delicate hair cells or to the auditory nerve itself.
And you mentioned earlier that this type of damage can be caused by exposure to loud noises.
Yes, loud noises are a major culprit. Those intense sound waves can literally tear the delicate hair cells apart, leading to permanent hearing loss. But it's not just loud noises. Aging is another factor. Just like other cells in your body, hair cells naturally deteriorate over time.
So even if you're careful about protecting your ears from loud noises, you could still experience some age-related hearing loss.
That's right. It's a natural part of the aging process for most people. And there are other factors as well. Certain genetic conditions can predispose people to hearing loss, and infections like meningitis or measles can damage the inner ear.
It sounds like there are a lot of potential threats to our hearing.
There are,
Hmm.
but that doesn't mean we're powerless. Being aware of the risks and taking steps to protect our hearing can make a big difference.
Absolutely. So for people with nerve deafness, what are the options?
Well, it depends on the severity of the hearing loss. For some people, hearing aids can be very helpful. They amplify sound, making it easier to hear conversations and environmental sounds.
And I've heard of cochlear implants. How do those work?
Cochlear implants are a remarkable technology. They're designed for people with severe to profound nerve deafness who don't benefit from hearing aids. A cochlear implant bypasses the damaged inner ear and directly stimulates the auditory nerve using electrical signals.
Wow, that's incredible. So it's like replacing the damaged hair cells with an electronic system.
That's a good way to think about it. It's not a perfect solution, but for many people, cochlear implants can dramatically improve their ability to communicate and engage with the world around them.
It's amazing how technology is giving people back the gift of hearing. So now that we've explored the causes and types of deafness, let's shift gears again and talk about how we assess hearing. You mentioned some interesting hearing tests earlier.
Yes, there are several tests that can help us evaluate how well your ears are functioning. Some of them are quite simple, while others are more sophisticated.
Let's start with the simple ones. I'm intrigued by these tuning fork tests, the Weber, Rinne, and Schwaback tests. They sound a bit old school, but I guess they're still useful.
Absolutely. They might not be flashy, but they're still valuable diagnostic tools.
Mm.
Think of them like the trusty screwdrivers in a toolbox. Sometimes the simplest tools are the most effective.
Okay, I like that analogy. So how do these tests actually work?
Well, the Weber test is a good starting point. It uses a vibrating tuning fork, which is simply a metal fork that produces a specific tone when struck. The tuning fork is placed on the top of the head, and the person is asked if they hear the sound equally in both ears.
And what does that tell us?
In someone with normal hearing, the sound will be perceived equally in both ears. But if there's conductive deafness in one ear, the sound will actually be louder in that affected ear.
That's counterintuitive. You'd think that would be quieter in the ear that's not working as well.
You'd think so, but it's because the blockage in the outer or middle ear prevents the sound from escaping, trapping it inside the head. This makes the sound seem louder in that ear, even though it's not actually being transmitted as efficiently.
Interesting. So the Weber test tells us which ear is affected, but it doesn't tell us what type of deafness it is.
Right. That's where the Rinne test comes in. It compares air conduction, which is how we normally hear, to bone conduction, which is the transmission of sound through the bones of the skull.
I remember learning about bone conduction in school, but I never really understood how it worked.
Well, imagine listening to music through headphones. That's air conduction. But if you put your fingers in your ears and hum a tune, you can still hear yourself. That's because the vibrations from your vocal cords are being transmitted directly to your inner ear through the bones of your skull.
Oh, that makes sense. So how do you use bone conduction to test hearing?
In the Rinne test, the tuning fork is first placed on the mastoid bone behind the ear, testing bone conduction. Then it's moved near the ear canal, testing ear conduction. In someone with normal hearing, air conduction is better than bone conduction, meaning they'll hear the sound longer when the tuning fork is near their ear.
But if there's conductive deafness, bone conduction will be better than air conduction?
Exactly, because that blockage in the outer or middle ear is preventing the sound from traveling effectively through the air.
And what about nerve deafness? What happens in that case?
In nerve deafness, both air and bone conduction will be reduced, but air conduction will still be better than bone conduction. This is because the problem lies in the inner ear or the auditory nerve, not in the transmission of sound through the outer or middle ear.
Okay, I think I'm starting to get the hang of this. So the Rinne test helps us distinguish between conductive and nerve deafness. What about the Schwaback test? You said that one compares the patient's bone conduction to the examiner's.
That's right. It's a bit more subjective than the other two tests, but it can still be helpful. The examiner places the tuning fork on their own mastoid bone and listens until they can no longer hear the sound. Then they immediately place the tuning fork on the patient's mastoid bone.
So if the patient can still hear the sound after the examiner can no longer hear it, that suggests conductive deafness.
Exactly. It means that the patient's bone conduction is better than the examiner's, which could indicate a blockage in the outer or middle ear. If the patient stops hearing the sound before the examiner, it suggests nerve deafness.
These three tuning fork tests, when used together, can really paint a picture of what's going on with someone's hearing.
They're a great starting point. But for a more comprehensive and precise assessment, we turn to audiometry.
Okay, let's talk about audiometry. That's the one with the fancy equipment, right?
That's right. Audiometry is like the high-tech diagnostic tool in our hearing toolbox. It uses an audiometer, a device that produces sounds of different frequencies and intensities to measure hearing thresholds.
So it tells us the quietest sounds a person can hear at various pitches.
Exactly. The results are plotted on an audiogram, which is like a map of a person's hearing ability. It's a very visual way to see the extent and type of hearing loss they might have.
I'm guessing audiometry is a lot more sensitive than those tuning fork tests.
It is. Audiometry allows us to test a much wider range of frequencies and intensities, giving us a much more detailed picture of a person's hearing. It's incredibly valuable for diagnosing hearing loss, monitoring its progression, and determining the best course of treatment.
It sounds like audiometry is an essential tool for anyone concerned about their hearing.
It really is, and it's becoming increasingly common for people to have their hearing tested regularly, especially as they get older.
This has been an incredible journey so far. We've covered so much ground, from the basic physics of sound to the intricacies of the auditory pathway and the challenges of hearing loss.
And we're not done yet. In the final part of our deep dive, we'll wrap up our exploration of hearing with some final insights and thought-provoking questions that will hopefully leave you with a deeper appreciation for this remarkable sense.
Welcome back to the deep dive. I don't know about you, but I'm still reeling from all the amazing things we've learned about hearing. It's such a complex and elegant system, yet it works so effortlessly that we just kind of take it for granted.
It really is a marvel of biology and evolution. And it's not just about the mechanics of sound transmission or the intricate neural pathways. Hearing is so deeply intertwined with our experience of the world, with our emotions, our relationships, our sense of self.
You're absolutely right. Think about the power of music to evoke emotions, or the soothing sound of a loved one's voice. Hearing connects us to each other and to the world around us in such profound ways.
And it's not just about passive reception. Hearing is an active process. We're constantly filtering and interpreting the soundscape, focusing on what's important and tuning out what's not. Our brains are working hard to make sense of all the auditory information that's bombarding us, creating a meaningful auditory experience.
It's incredible how much processing goes on behind the scenes without us even being aware of it. It makes you wonder how much we're missing, how much of the soundscape is just slipping past our conscious awareness.
That's a fascinating question. There's a whole field of research dedicated to studying how our brains filter and prioritize auditory information.
Yeah.
And it turns out that our attention, our expectations, our emotional state, all of these factors can influence what we hear and how we interpret it.
That makes sense. If you're engrossed in a conversation, you might not even notice the traffic noise outside, even though it's objectively louder.
Exactly. And think about how a piece of music can sound completely different depending on your mood. The same notes, the same harmonies, but the emotional impact can vary widely depending on your internal state.
So hearing is not just about the physics of sound, it's also about perception, interpretation, meaning making. It's about how our brains construct a world of sound from all those raw sensory inputs.
Precisely. And it's this subjective, interpretive aspect of hearing that makes it so fascinating and so challenging to study. We can measure the physical properties of sound waves, we can map the neural pathways involved in auditory processing, but ultimately the experience of hearing is something that's unique to each individual.
Well, this deep dive has certainly given me a newfound appreciation for the complexity and wonder of hearing. What are some of the key takeaways that you hope listeners will walk away with?
First and foremost, I hope they'll have a better understanding of how hearing works. From the basic anatomy of the ear to the intricate neural pathways that carry sound information to the brain, it's a system that's both remarkably resilient and surprisingly vulnerable.
Yes, that's something that really struck me. We learned about all the potential threats to our hearing, from loud noises to aging to certain medications.
Right, and that brings me to another key takeaway. We have to be proactive about protecting our hearing. It's a precious sense that we often take for granted, but once it's damaged, it can be very difficult, if not impossible, to restore.
What are some simple things that people can do to protect their hearing?
Well, one of the most important things is to be aware of the volume levels you're exposed to. If you have to shout to be heard over the music or the noise, it's probably too loud. And if you're using headphones or earbuds, keep the volume at a safe level and take breaks to give your ears a rest.
That's good advice. What about those foam earplugs that you see at concerts and sporting events? Are they effective?
They can be very helpful in reducing noise exposure,
Yeah.
and they're inexpensive and easy to use. I always recommend keeping a pair handy, especially if you know you're going to be in a noisy environment.
And if someone is experiencing hearing loss, what should they do?
Don't hesitate to seek professional help. An audiologist can evaluate your hearing and recommend the best course of treatment, whether it's hearing aids, cochlear implants, or other interventions. The sooner you address hearing loss, the better the outcome is likely to be.
So prevention is key, but early intervention is crucial as well. Any other final thoughts you want to leave our listeners with?
Well, as we've discussed, hearing is much more than just a physical process. It's a gateway to our social world, our emotional world, our intellectual world. It shapes how we experience and interact with everything around us. So pay attention to the soundscape. Appreciate the nuances of sound, and be grateful for the gift of hearing.
Beautifully said. It's been a privilege to explore this amazing world of sound with you. Thank you so much for sharing your expertise with us.
It's been my pleasure, and thank you for the opportunity to delve into such a fascinating topic.
And to our listeners, thank you for joining us on the deep dive. We hope this episode has left you with a newfound appreciation for the wonder and complexity of hearing. If you're interested in learning more, be sure to check out the show notes for links to additional resources. Until next time, keep listening. I start